All right, hi everyone. So the topic for this chapter is chapter 4, sensation and perception. We'll look a little bit at what is sensation, what is perception, looking at the different cells and thresholds and subliminal messages that are involved. We'll definitely spend a little bit of time looking over the five senses, predominantly vision, but looking at all five of them, and then a little bit with perceptual organization and also illusions at the end. So the main topic that we're looking at this week is how do we construct our representations of the external world? And in order to represent the world, we must first detect physical energy from the environment and convert it into neural signals. And we do this through a process called sensation. We begin with some kind of external source from inside, either from outside of the body or inside the body. It's going to stimulate a receptor cell in one of our sense organs, and then the process of sensory stimulation has occurred. We then go through the process of selecting, organizing, and interpreting those sensations in a process that we call perception, kind of organizing and making sense of what we have picked up from the world around us. And we're constantly doing this all the time, sensation followed by perception. Now, when we're detecting information from the world around us, we have some things that we call thresholds. And one of them is called an absolute threshold. It's the least amount of energy that can be detected as a stimulation 50% of the time. Anything below our threshold won't be experienced. And psychologists present stimuli at different intensities, asking people whether they see it or hear it. And the threshold is detected at the point where we can detect that stimulus 50% of the time. It's going to differ from person to person, even from moment to moment. Think about, for example, like a hearing test, where you put those headphones on your ears and they play the tones and you raise your hand every time you can hear it. They're going to detect the point at which you can hear that sound 50% of the time, and that's going to be your threshold for hearing, or your threshold for sight could be calculated as well. Now, to complicate it a tiny bit, under normal conditions, our thresholds can vary a little bit from moment to moment, from person to person, and we can also influence them through a process called adaptation. It's an automatic adjustment of our senses to the overall level of stimulation in a particular setting. So think about, for example, if you had a Band-Aid on your hand, you would be very aware of that Band-Aid, right, for a period of time, but after a certain period of time, it's like you get used to it. Your body adapts to it and you no longer notice its presence. Think about a bag of salty potato chips. I have a bag of chips there on the slide. Those first few chips are so salty and so delicious. And the more that you eat them, the more you adapt to that level of salt, and they kind of become slowly less and less salty over time. So if you think about these things, right, we tend to have thresholds that rise and lower because of our senses. They're constantly adjusting or adapting. And this kind of leads to an interesting phenomenon, which is subliminal messages or subliminal perception. Subliminal messages are things that are below our level of awareness. Think about advertisements, right? They used to flash popcorn and soda signs up in movie theaters to see if they could get people to buy more concessions. Didn't necessarily affect anything. It had kind of like fleeting effects, but nothing enduring. So typically, what we tend to think is that if something is presented under your level of awareness, under your threshold, it isn't necessarily noticed. It's not going to have any kind of long-term effect, but maybe it could prime you to a response. Kind of an interesting area of investigation and study within this area. But we definitely do have thresholds, and they can change constantly due to that process of adaptation. Now, what we'll go first is we'll look a little bit at the eye, kind of our most dominant sense, which is vision for most people. And if you look at kind of a typical image of the eye here, you can see lots of different parts, and they're covered really well in this little diagram here. But the eye has a front area called the cornea, that transparent protective coating over the front part of our eye. And if you go in from the cornea, then we have the pupil, a small opening in the iris, and this is where light is going to enter the eye. The iris is the colored part of the eye that regulates the size of the pupil. In bright light, the muscles in the iris are going to contract to make the pupil smaller, protecting the eye from damage. And in dim light, the muscles relax to open the pupil wider, let in more light, make it easier for us to see. Excuse me. We also have the lens. Fighting the end of a cold here. We also have the lens, the transparent part behind the eye, which allows the pupil and focuses the light onto the retina. Right, the lens is normally focused kind of in the mid distance, and it can change shape or accommodate to focus on things that are either closer or farther away, depending on what our goal is. If we move inward a little bit into the eye, we have a layer called the retina. Now, the retina is our light-sensitive inner surface of the eye that contains the receptor cells sensitive to electromagnetic energy and help us process visual information. So it contains two types of receptor cells, which are named for their shape. We have the rods and the cones. Now, the rods are the receptor cells in the retina that are responsible for night vision and the perception of brightness. They're highly sensitive to light, and we have about 120 million of them in each eye. The cones, on the other hand, are the receptor cells in the retina responsible for daytime vision and color vision. They're only moderately sensitive to light. They're most useful during the day. And then we tend to have about maybe 8 million or so of each of those in each one of our eyes. So as the messages are constantly coming into our eyes, which is constant, again, it's happening all the time, the messages from our eyes must travel to the brain in order for any kind of visual experience to occur. And in order for that to happen, they're going to be transmitted through a bundle of axons of ganglion cells carrying neural messages from each eye to the brain. And that bundle of axons is called our optic nerve. The optic nerve is what's going to help transmit that information back to the brain. Now, interestingly, we do possess a blind spot, kind of like when you're driving in a car, there's a little bit of a blind spot. There is a place on your retina where the axons of all the ganglion cells leave the eye where there are no receptors. And as a result of this, we get these kind of spots in our brain where there is no image. We also have something called the optic chiasm. This is the point near the base of the brain where some of the fibers in the optic nerve from each eye are going to cross to the other side of the brain. Now, the messages do cross over, so everything going to the left eye is going to go to the back of the right visual field, and then from the right to the left, everything crosses at this chiasm. And again, we do have that little bit of a blind spot, which creates some really kind of interesting effects, which you can definitely test for. And there's some really cool YouTube videos that I've seen on that as well, if you wanted to take a look. We have a couple of interesting theories of color vision as well, kind of two main ones as to how do we see color? How do we take in and process and see everything in the world around us? The first one is called the trichromatic or Young-Helmholtz theory. This is the theory of color vision that holds that all color perception derives from three different color receptors: red, green, and blue. We also have the opponent process theory, which holds that we have three sets of color receptors: a yellow-blue set, a red-green set, and a black-white set. And this allows us to then determine what color we experience, and it leads to kind of a cool phenomenon that we can call color after images. And here's an example of one for you here. So the opponent process theory, when you stare for a long time at one color, your eyes are going to kind of become fatigued to that color and then respond vigorously to the opposite. So if you were to stare at the white dot in the middle of this image for a matter of like 30 seconds. So as I'm talking, be staring at that white dot. Your brain, as you're staring at this, is going to be taking in the green stripes and the red, green, and all of these things are going to be coming in. And then in a second, I'm going to switch to a blank white piece of paper, and your red-green receptors are going to respond vigorously to red wavelengths, and you're going to see red. Okay, so here we go. So I'm going to flash to a new page. And you should have, for just a second, seen a color after image of a red, white, and blue flag. I have a couple more of these. This one, I want you to stare at the eye of the parrot, right? So as you stare at this parrot's eye, again, your brain is firing, staring at the red. And then eventually, if you look over at the cage, you'll kind of see almost like a moving image of that bird translate over into the cage, right? And you start to see an opposite. It's almost like a reddish green kind of color because of that opponent process theory. One more for you. If you had poor luck with the red, maybe you'll have better luck with the yellow and the blue. So stare at the yellow stripes on the fish and just focus on them. Keep staring at them while I'm talking. And then when I tell you, you're going to look over at the vase and you'll be able to see kind of a color after image of that fish in the vase. And again, all of these things are support for the opponent process theory, but there's also a lot of support for the three color or trichromatic theory as well. As we move on to sound, another very important sense, right? Hearing begins when sound waves are gathered by the outer ear, right, and passed along to the eardrum, causing it to vibrate. The vibration of the eardrum causes three tiny little bones in the middle ear to vibrate: the hammer, the anvil, and the stirrup, the tiniest little bones in the body. And then once these create these messages go to higher level parts of the brain, primarily the temporal lobes, which allow us to make sense of everything that we've taken in. Now, so we can determine the location of sounds by what the intensity and timing differences in which sounds hit our different ears. Lots of different causes of deafness. Deafness can result from ear infections with fluid backup or buildup, preventing vibration. Somebody can be born deaf. There's a lot of reasons that people can be deaf that are largely unknown, like nerve damage to the auditory nerve, puncturing the eardrum, repeated exposure to loud noises, like going to too many loud concerts. But hearing is a very crucial sense for a lot of people, allowing us to take in the sounds of the world around us through the vibration coming in through our ears. We also possess the sense of touch. The skin is our largest sense organ. A person who is 6 feet tall has 21 square feet of skin. That's a lot of skin. Our skin protects us from the environment. It holds in bodily fluids, regulates our internal temperature, contains receptors for our sense of touch, which plays an important role in human interaction and emotion, like hugging and kissing and handshakes and so on. Our skin receptors, all of that skin that we have kind of four distinct skin senses that they can detect. They can detect pressure, warmth, cold, and pain. And pain is one of those things that cause a lot of problems for people. More people visit the doctor for pain than any other reason, and yet it still remains a little bit of a mystery. A lot of thought is that pain is nature's way of telling us that there's something wrong, but physical injury isn't always accompanied by pain, just to complicate that a little bit. And there are conditions where people are born with an insensitivity to pain. There's something called SIPA, congenital insensitivity to pain with anhidrosis, where a person lacks any kind of sweating response or sensation of pain starting at birth. But for most people, four different distinct senses, lots of square foot of skin, and it's a very large, important sense organ. Our next biggest organ here, sense organ, is that of taste. Our taste buds, which allow us to detect different flavors and tastes, are the structures on the tip of our tongue, right? You can find them on the tip, the sides, and the back of the tongue, actually. And all in all, we have 5 different basic taste quality receptors: sweet, sour, salty, bitter, and umami, right? Umami kind of being like more of like a poultry or kind of MSG kind of flavor. But all of these are on our tongue. The chemical substances in food are going to dissolve in our saliva, go into the little crevices between the papillae on our tongue. And when they come in contact with our taste buds, they release neurotransmitters that cause adjacent neurons to fire, sending nerve impulses to the parietal lobe of the brain and then to the limbic system. So a lot of different flavors and taste qualities that we can possess, specifically 5 of them, but they can combine together for infinite combinations. Like taste, we also have the sense of smell, and smell is also a chemical taste, or a chemical sense, I'm sorry. Odorants enter our nasal cavity to stimulate up to 5 million different receptors to allow us to sense smell. And what happens is once it comes up through our olfactory bulb, or up through our nose, it goes to the olfactory bulb up in the brain, our smell center of the brain. And this plays a huge part in allowing us to then give it meaning and process it, right? This is the smell center in the brain and plays a huge role in smell and memories, something that you'll be looking at as part of our discussion this week. You'll be reading a little bit more about it and learning a little more about it there. We also have our kinesthetic and vestibular senses. Kinesthetic senses are our senses of muscle movement, posture, and strain on our muscles and joints, versus our vestibular senses give us a sense of equilibrium, our body position in space. It helps us determine which way is up, which way is down. Most of the time, we don't notice these senses when they're operating properly, but we do notice them under moments of motion sickness. If you get sick in a car or when you're traveling on vehicles, get this disconnect between your senses and the movement that you're experiencing, or if you experience anything like vertigo. Both of those things tend to be moments where you really notice these senses quite predominantly as they're not quite functioning properly. A little bit about perception on the other side of the sensation and perception coin. With perception, what we're looking at here is our senses kind of understanding and interpreting the world around us. So perception involves deciphering meaningful patterns in the jumble of sensory information. It's our brain's process of organizing and making sense of all of this sensory information that comes in. Now, perceptual organization was something that was really formulated by a group named Gestalt psychologists back in like the early 20th century. Gestalt translates to mean whole or form or pattern, and it was believed that, according to this group of psychologists, that the whole is greater than the sum of its parts, and that it kind of helps us to distinguish the world around us. And so what we see here is we get these interesting kind of phenomenon with figure ground phenomenon. We have a tendency of our visual system to simplify a scene into kind of the main object that we're looking at the figure, and then everything else in the background, which we would call the background or the ground. And so we get these images like these ones here, and you're going to be drawn to one or the other right off the bat. Do you see a man with a saxophone or a woman's face? Do you see two faces staring at each other or a vase in the middle? Do you see a larger, older face or kind of a younger face looking off to the side? And so we get these interesting figure ground illusions or sometimes even illusions or perceptions that can come from kind of ambiguous cues related to figure and ground. Another interesting thing about perception is we tend to group things or organize stimuli into coherent groups. And we have four main principles of perceptual organization or grouping. Rather than seeing a bunch of separate lines, we tend to group these together because they're closer or more proximal to each other. We tend to group things that are similar, like a group of triangles or circles, right? And then we tend to also look at things as one continuous line or two continuous lines and these as connectedness rather than separate entities. One more thing that can come out of all of this are visual illusions. Sometimes as a result of some of these false and misleading depth cues and different cues from our perceptual organization, we can end up with kind of a false or misleading depth cue about the world around us. Physical illusions is when something with the behavior of light before it reaches the eye causes us to see something that isn't physically there. This is kind of like a mirage on the road, right? That can sometimes happen. Versus perceptual illusions is when we have misleading cues that give rise to inaccurate or impossible perceptions. So for example, this line and this line are the exact same length, but this one looks quite a bit longer because it's pointed outward. Or this circle right here and this circle here are the same size, but the context around them tends to distort it. And a really famous example of this is the Ames room illusion, which I talked a little bit more about in the textbook. A couple of other things, we can also get illusions with movement, right? So real movement is when you physically displace something from one location to another or one position to another, like if you pick something up and moved it. But we can get what's called apparent movement, when things are actually standing still, but it looks like they're moving. And one of the ways that this can show up is something called stroboscopic motion, when we get a series of still pictures in a rapid succession. And this is how we used to make motion pictures, kind of like this one, where you take a bunch of pictures in rapid succession and it looks like something is moving. We also have something called the five phenomenon, which we get a lot with flashing light sequences, like with Christmas lights or lights on billboards, like in Las Vegas, where it looks like there's movement because the lights are flashing very rapidly in a sequence on a theater. A couple of other things as we kind of near the end of the perceptual unit here. How important is our experience in shaping our perception? We each possess something called a perceptual set, a mental predisposition to perceive one thing and not another. So, for example, depending on the context of what we're seeing, we might see flying saucers or clouds, a tree trunk, or the Loch Ness monster, right? Our perception and what we're expecting and what we're thinking about can play a really huge role in deciding what it is that we see or what it is that we give meaning to. One kind of last big area within perception is extrasensory perception, or ESP, the ability to perceive or acquire information without using our ordinary senses. And sometimes we call this the field of parapsychology, where we're studying ESP and kind of other related phenomenon. And as fascinating as ESP is, things like being able to read somebody's mind or tell the future or move things with our mind, there is no clear scientific support for the existence of ESP. It's considered a pseudoscience, which we talked about in chapter 2. Really interesting. Some people claim to be able to do it, but it has never held up under scientific testing. Chance alone would guarantee that we're going to have some coincidences, but they don't tend to hold up under scientific scrutiny. Lots of different types of ESP. Here are some of the most common ones. Things like telepathy, where one person is sending thoughts and another person receives them. Clairvoyance would be when you can perceive things that are happening somewhere else, like you sense that your friend's house is on fire, and it is. Precognition would be when you perceive future events, such as like a plane crash or an accident, made famous by the Final Destination movies for sure. And then psychokinesis, where you can move things with your mind. And again, as interesting as all these things are, they have yet to hold up under scientific scrutiny, but they're definitely kind of an interesting side note related to this chapter. So that is chapter 4, kind of short and sweet, looking at sensation and perception. As always, don't forget to read the chapter in the textbook and to go through the lecture that I created for you. Thank you so much, and I'll see you for the next one.